So unfortunately, the next speaker, you are the first speaker, first author of the next talk cannot make it. So Xiong will cover this topic on behalf. Okay, please start.
Hi everyone, this is Wang. Due to visa issue, the authors are not able to come to this conference. I will present this work, UQRCom, Underwater Wireless Communication based on QR code. Underwater operation plays a critical role in underwater rescue, bridge inspection, and ocean exploration. When divers are in underwater environment, the communication among them is pivotal to ensure efficient cooperation and operation safety. However, underwater communication is challenging and very different from communication in the air. Divers cannot directly talk to each other as their faces are covered by heavy and bulky diving helmets. The most popular communication technique is to use radio frequency RF signals. RF-based communication such as Wi-Fi and LTE has achieved great success in the air. However, it doesn't work in underwater environment due to the severe signal attenuations. For example, Wi-Fi signal can only propagate about 0.5 meters in water. Surprisingly, in the 21st century, gestures are the most popular way for underwater communication between divers. It has many inherent disadvantages. Each individual has his or her own way of gesture expression, which can cause ambiguity. Also, gesture communication has limited working distance and incurs a large latency. With all that background, we propose our method, UQRCom for underwater communication based on QR code. QR code is the most widely used one among all types of two-dimensional codes. It can store a large amount of data and has quick response speed. At the same time, QR code has strong error correction capability, which is ideal for harsh underwater environments. However, QR code will face unique challenges in underwater environments. For example, the water flow makes it difficult to quickly locate the QR code and capture complete QR code. How to modify existing QR code design to address the unique challenges in underwater environments is our first challenge. Our system works purely in underwater environment. The sea and the lake water cause low visibility and color degradation. Traditional imaging processing method cannot meet the strict latency requirement for real-time communication. Designing a lightweight imaging processing scheme tailored for the proposed communication system is the second challenge. During the underwater operations, divers usually wear a lot of dedicated equipment. We do not want our system to add further burden to the diver. How to make the proposed system work on lightweight resource-constricted potato device is our third challenge. We designed a new QR code, named UQR code in this paper. UQR code improves multiple models to make it suitable for underwater environments. First, we remove the alignment patterns. The main function of the alignment patterns is to resist the distortion of the UQR code when it is printed on the workcode paper. As our UQR code will be displayed on the screen, we remove the unnecessary alignment patterns. Secondly, we enlarge the position detection patterns on the upper left, upper right, and the lower left in the UQR code. The purpose is to increase the communication distance of the proposed system. In harsh underwater environments, the QR code can be partially blocked. The more error correction codes, the stronger capability of the QR code can fight against interference and blockage. Hence, we increase the redundancy of error correction codes. Finally, we also adjust the color of the UQR code model. This kind of color arrangement maximizes the green value difference between the QR code models and the background color. In this way, we can further increase the communication distance. We conduct experiments in different water environments, including spring, lakes, CA, CB, and CC, both during day and night periods. As shown here, CA has a low turbidity, CB has a medium turbidity, and the CC has a high turbidity. Now, let's visualize the experiment results. We can observe that both UQR code and QR code achieve the longest communication distance in spring water. Furthermore, the communication distance at night is always longer than that during the day. This is because compared to the daytime, there is no sunlight interference at night. To verify the effectiveness of our UQR code color design, we implement different color of UQR codes and tested their performance in spring waters of different colors. We can find that our proposed color arrangement always achieves a longer communication distance and a lower CER in all spring waters. The previous results are based on QR code of smart screen size. If we increase the size of the QR code, the communication distance can be significantly increased. For a QR code of 14 by 14 centimeter size, the communication distance can reach 19.5 meters in clean water. With all that, let me conclude our paper. This is the first work realizing underwater communication based on QR code. We propose novel design to address unique challenge in underwater environment. We conduct comprehensive experiments to demonstrate the effectiveness of the UQR code. Thanks for listening.
Thank you very much. Do you also cover the Q&A?
Sorry, I don't know the detail
Okay.
of the paper.
Don't worry. Please, if you have any question, please directly contact to the authors. Okay, so the next talk is actually her own work. And if you are prepared, please start.
So this is my work. Okay. Hello, everyone. Good afternoon.
The screen is not ready yet. Could you try to?
Wait. Okay. Hello, everyone. Good afternoon. This is Wang from Peking University, China. This is a joint work titled WiMeasure, Millimeter Level Object Size Measurement with Commodity Wi-Fi Devices. Wi-Fi-based sensing have attracted a lot of attention from both industry and the academic. Researchers have explored different applications, such as tracking, location, gesture recognition, and respiration monitoring. However, measuring the size of an object using no frequency and narrowband Wi-Fi signal is still a challenging issue. In our work, we want to address this issue. Specifically, we let the target traverse the line of sight path between the transmitter and the receiver, and then we use the diffraction effect to measure the size of the object. How do we do it? Firstly, when the object travels line of sight between the transmitter and the receivers, we develop a diffraction model. The received signal can be represented through integration, as in the equation. And the parameters are shown in the figure on the right. It's worth noting that the received signal not only contains the information about the target's position related to the transceivers, but also includes information about the object size. Therefore, we have the opportunity to extract the object size from the received signal. Fortunately, we also observe some interesting phenomenon. When the path difference between the upper and the lower boundary of the object is the multiple of the signal wavelengths, we can see a sudden change in the direction of CSI signal on the IQ plane. We like to call this point singularity. Remember this, it's very important. Furthermore, as the object moves upwards from the line of sight, the path length difference gradually increases from 0 to 1 wavelength and lead to the first singularities in the CSI signal. And when the path length increases to 2 wavelengths, the second singularity appears in the CSI signal. If the transmitter and the receivers are set up in a fixed position, which means the line of sight distance is fixed, and the object moves a fixed distance, and which is very easily to achieve. So the larger the object, we can say there are more singularities appears. Therefore, by counting the number of singularities, we can roughly estimate the size range of the object. For example, when the line of sight is 0.5 meter, we can categorize object size at 4 centimeter intervals. Now, when we keep the object size constant at 24 centimeters, and we change the setup of the transceivers, which means we adjust the line of sight distance, and the number of singularity decreases with the line of sight distance increases. For example, when the line of sight distance is 1 meter, we observe 3 singularities in the IQ plane. While at 1.5 meters, we found 2 singularities. It's very interesting, right? And at 2 meters, only 1 singularity appears. So by leveraging the variations between different line of sight device pairs, we can enhance the accuracy of object size measurements through the collaborative use of multiple pairs of Wi-Fi devices. And we found that the more devices we use, the higher our measurement accuracy becomes. Therefore, we can achieve object size measurement with arbitrary accuracy. At the same time, we implement an object size measurement system called Y-measure and conduct a comprehensive evaluations. For object size classification, we use a single pair of devices to categorize various everyday items, achieving about 100% classification accuracy. And for the fine-grained object size measurements, we use 1, 2, and 3 pairs of devices. And the more devices we use, the higher the measurement accuracy. In all cases, the median error consistently reaches the millimeter range. In conclusion, in this work, for the first time, we demonstrate that it's possible to accurately measure an object size use low frequency and narrow band Wi-Fi signals. And we also and a novel theoretical model is proposed to characterize the quantitative relationship between the number of singularities on the Wi-Fi CSI signals and the object size. Also, guided by the model, we design and implement a size measurement system on commodity Wi-Fi devices. The proposed system is able to achieve a surprisingly high accuracy, that is 2.6 millimeter, and is robust against environment, material, and speed diversities. Thanks for your listening. That's all.
Thank you very much. Any questions? Yeah, I think that you have built interesting practical application based on the very interesting phenomenon which happens on the physical, caused by physical phenomenon. And I'm wondering how you discovered singularity actually happens on IQ plane, because you don't usually measure such kind of trajectory.
You mean how to observe this phenomenon?
Yeah, how did you find this interesting phenomenon?
By experiment. And we found that the singularities numbers is very related to the object size. And we just have a research on the diffraction effect and found this phenomenon. Yeah.
Fantastic. Thank you. Any questions?
This is Wang from Michigan State University. As you previously mentioned, with the increasing of the total number of the device, the prediction error will decrease. So are there exist any limitation for the total number of the device?
You mean which millimeter leveled object size measurement use how many devices, right?
Yeah, correct.
In this experiment, if we just want to classify the object size, we only need one single pair of transmitters and receivers. But if you want to achieve a more accuracy, a higher accuracy, you need more device. And you can see in this slide, let me see. Yeah, if you have two pair of transceivers, the error will less than 0.66 centimeter. Yeah, this is the results.
Okay, thank you very much, and thank you very much for 2 talks. Okay, 5th speaker is Yang Su from Michigan, University of Michigan.